Welcome to another College Algebra tutor training video. This video is about 8 different types of functions. Your students who are taking College Algebra will need to be very familiar with all of these functions, so do you. As part of this assignment, you will fill out the same chart that they do in their classes for all of these functions. Before we begin, we need to talk about the 5 different ways to describe a function. One is just by its name, right? Linear, quadratic, exponential. When you say that, you want to have some things come to mind about that function family. The equation, there's things to notice in an equation, like a square root, tells you there's a square root function, for example. Graphs, you notice the certain shapes of the graphs, whether they have asymptotes, things like that. Their data, you can look at slopes and differences and see if you can guess what kind of function it is from that. And lastly, the way that it's used in real life to fix problems. So we're going to look at all of those 5 things today in this video. First, let's just start with linear functions. Looking at their equations, you'll be able to recognize these. We've talked about them before in previous videos: mx plus b, standard form, and point slope form. Graphs are all, you guessed it, lines. And one thing that's new here is you may not have heard before the term first difference and second difference. Let's talk about that. So in the data, you can tell that they're going up by 2 in the y values and up by 1 in the x values. The first difference is found by taking the y values and subtracting them. Looks a little bit like slope because that's what it is. For a linear function, the first difference is always the same. It is a constant because it has a constant slope. For the application, this is going to be your job. I'm not going to tell you. You're going to have to do some research. For each of the functions, I want you to do the research and figure out an application for real-world use of those functions. Give it a try. Alright, absolute value functions have in their equations absolute value symbols. There you go. The graphs all have their unique V. Could be upside down or right side up. In the data, again, we're going to look at first difference. You'll notice there's a point, which is actually the vertex, where the data changes from a negative to a positive because that's where it changes direction, right? That's where the slope changes. For that reason, our V shape always has either a maximum or a minimum y value. And again, have fun looking up that application. Alright, quadratic functions have something being squared, the variables being squared somewhere in there. Now you'll notice on these equations, these ones look more different than the other ones have been so far. On the first one, this is called vertex form. You'll notice any equation that has h and k is really talking about transformations. We'll talk more about transformations in a later video. But the other ones just have a, b, and c as placeholders. In the second equation, the parentheses have been multiplied out and it's been simplified into a trinomial. You will see them written either way. Graphs have a U shape, a parabola, could be upside down smiley faces or frowning faces. Alright, let's look at first difference. Notice, unlike a line, the first difference of a quadratic function is not constant, but something called the second difference is. Well, the second difference is it will take one set of first difference, so a negative 9 minus the one next to it, and it will always give you 2. So for quadratic functions, the second difference is always constant. If you have taken or are familiar with calculus, this is going to feel a lot like a derivative, aka differential, aka difference. Right? This is really what it's finding is derivatives. And so for a linear equation that we saw earlier, that's going to be a constant first difference, but for quadratic functions, the second difference is constant. And your application you'll find. Oh, sorry, I forgot to say, just like with the absolute values, this one does have a maximum or a minimum value for y. Square root functions have, in the equation, square roots. And it'll look like somebody took a parabola, turned it on its side, and cut it in half, because really that's what happened. Square roots are inverses of parabolas, so they have a similar shape to them. But notice gets cut in half, and here's why. Looking at the data, it's a little bit easier to see. You have these things. Oh no, Excel told me hashtag none. That's because I cannot in Excel or on a graph have imaginary numbers, so I can't take the square root of a negative. So we don't have any first differences or second differences in this data, but you should have some numbers that you can't plug into X because that will give it a negative, right? So that's why its domain is limited, right? It has this point here and nothing goes below that point in the parabola. Exponential functions have a variable in the exponent of a base, a constant base, and they look like this. They are going up very, very steeply, exponential shape. And the data, okay, I had to make a bigger table for this one. Right? So first I have my x values and y values. The first difference, obviously, not constant, not great. Ratios, what a ratio is, this is taking one y value and dividing it by the next y value. Again, not constant. But if you do that with the values of the first difference and one next to it, right? First difference divided by first difference. So if we're going to do like 4, looking down here, 4 divided by 2, for all of these, that is actually 2. And again, so we have a constant ratio of first difference. This one is going to be constant for exponentials. And interestingly enough, that 2 is actually the base. So this is the data table for an exponential function that has a base of 2. So, pretty cool. All right, and you can think of some cool applications for exponents. All right, now, of course, oh, I forgot. How did I forget the asymptote? Exponential functions have horizontal asymptotes because they get really, really close to that number but don't actually cross it, like 0. It's not always 0 though. So on this first graph, this one is 0, but this one has, the second graph has been shifted up. There's an asymptote there. So it gets close to that number but never reaches it. Logarithmic functions, we have to do the opposite, right? If we do quad x, we have to do square roots. If we do exponential, we have to talk about logarithm, because they are inverses. Equations have a logarithm in them. Surprise! The graphs, right, go up slowly. Right? They are also the inverses of exponential. So you can see a similar shape, but it is in a different direction. So again, as we were just talking about exponential functions having horizontal asymptotes, logarithmic functions actually have vertical asymptotes. You can see them right here. Looking at the data, it will reflect that, right? Again, just like with square roots, we can't plug in negative numbers or 0. Logarithms, you can't plug in 0. You can take the square root of 0. That's just 0. But you can't take a log of 0 and get a number. Not real. Frowny face. But you will look for those ones that you can't plug in, and you'll notice that it has a vertical asymptote, something that it will get close to. Alright, this one is fun. I didn't learn about these functions until I taught this class. It's really interesting. You don't see them very often, but they are pretty cool. Logistic functions are like a mix of a rational function, which we'll talk about in a minute, and an exponential function, right? We've got a variable inside the exponent, but we also have the whole thing as a fraction, and then it's got something added right there. Logistic functions will always have the 1, the base will always be e, the number, and the other things can change, but we'll have x in the exponent there, but it'll look like this. The graphs look like somebody took an S and stretched it out, right? So it's pretty flat, steep, and then flat again. The middle part looks like an exponential, and then it just decides to not be exponential anymore as it goes to the other direction. So it goes steep in the middle, and it flattens out on either side. Because it flattens out, you can already probably guess that there are actually 2 horizontal asymptotes, one below the S shape and one above where they flatten out. No differences or ratios, nothing constant. But you want to look for 2 horizontal asymptotes. So for example, in this one, this y value on top is getting close to 0, and this one is getting close to positive 10. So those are the two horizontal asymptotes. So that's something you can notice in the data. Okay, last one. I actually have one more surprise for you. We talked about rational functions in the previous video. So you already know the answer to all of these. You can figure this one out on your own. I'm not going to tell you. So your job after watching this video is to go and fill in the application for all the other functions and this one, and then you can fill out how do we tell a rational equation, and what do the graphs look like, and what are the data? How could I recognize it in the data? So go ahead and fill out that chart and do some research, and well done. That's it.